Today we are going to discuss enhancement and depletion type MOSFETs. I am Dr. Imran Khan. For more videos and technology updates, please subscribe our channel. If you have any question related to our video, please don't hesitate to contact me. MOSFET is metal oxide semiconductor field effect transistor. In MOSFET, we apply the voltage at the gate terminal and control the current between drain and source terminals. MOSFET is unipolar device because it has only one type of carriers, either electrons or holes. Why do we use MOSFETs? MOSFETs are used extensively in integrated circuits and other electronic devices due to its smaller size, because they are simple to manufacture and we don't need biasing resistors, and they are used extensively in VLSI, very large scale integration circuits. The enhancement type MOSFET is the most significant semiconductor device available today. MOSFET or metal oxide semiconductor field effect transistor has been extremely popular since late 1970s. If we compare MOSFET with BJT, MOSFET has a lot of good characteristics compared to BJT. It can be made smaller, it is easier to fabricate, it has simple circuitry for digital logic and memory, and it has more inferior performance in analog circuits. So the MOSFETs are used extensively in integrated circuits, and we no longer use BJT. Also, MOSFET is faster than BJT. So before going to enhancement and depletion type of MOSFET, we will discuss the simple device structure of field effect transistors. So in the figure 1, you can see the perspective 3D view of simple field effect transistor, and in the figure B, you can see cross-sectional view of a MOSFET structure. So in the figure 1, you can see the perspective view of a MOSFET. So this upper terminal is the gate terminal, and this is the source terminal and drain terminal. So this is NMOS transistor. So you can see this N plus diffusions on the source and drain regions. So here you can see this is the channel region, and this is channel length, channel width, and here you can see an insulator. So this is silicon oxide or SiO2. So gate is connected to this channel region via this insulator. That's why the gate current Ig is always 0 in case of MOSFET. So this is the cross-sectional view of the MOSFET. So here you can see this is the gate terminal, again source and drain terminals, and this is the channel region. Because this is NMOS transistor, so its substrate is p-type substrate, and this is the fourth terminal, body terminal. But for the simplicity in our calculations, we don't include the body terminals. So here you apply the voltage at the gate and control the current between drain and source. So this is the basic operation of a simple field effect transistor structure. Now let's discuss the physical operation of an enhancement type of MOSFET. So enhancement type of MOSFET, we need to induce a channel first, and then the current flows between drain and source. So here you can see operation with no gate voltage. So when there is no gate voltage, then obviously ID is equal to 0 and the device is in cutoff region. So when we start applying this gate voltage here, electric field generates and it attracts the electrons in this region and repel the holes. So if we keep on increasing this gate voltage, more electrons appear here until this Vg is lesser than Vt. When this Vg becomes equal to Vt, then an inversion layer introduced here. But still there is no current because our source and drain are grounded. But when we apply some drain voltage, we already have applied this gate voltage, and our gate voltage is Vg is greater than Vt. So here when we apply this drain voltage, current starts from drain to source. So this is the basic operation of an enhancement type of MOSFET. We first induce the channel and then we apply the drain voltage, and then the current flows between drain and source terminals. So here you can see that applying a small VDS. So first your source is grounded and you have applied some gate voltage here, and you have applied some drain voltage here. This Ig is always 0 because the gate is connected to this channel region via an insulator. So when we apply this gate voltage and our Vg is greater than Vt, then a channel is induced here. And when we apply this VDS, current starts to flow between drain to source terminals due to the potential difference. So applying a small VDS from 0.1 to 0.2 volt causes a current ID to flow through the induced N channel from drain to source. So here you can see this scenario. So the magnitude of this drain current depends on the density of electrons in the channel, which in turn depend on VGS. For VGS is equal to VT, the channel is just induced and the current conduction is negligible. If your VGS becomes greater than Vt, then the depth of induced channel increases and ID will be proportional to VGS minus Vt. So this VGS minus Vt is known as effective overdrive voltage. So this in case of your MOSFET, always your Ig is equal to 0. So here you can see your enhancement type of MOSFET. So how we can form the channel and how the current flows in an enhancement type of MOSFET. So this will be explained here. So first you can see that you have grounded the source and the drain terminals, and you have applied some gate voltage here. So when your Vg is equal to 0, no current will flow. If you start applying this Vg because of the electric field, this Vg is a positive voltage, so it will attract the electrons on this surface and repel the holes. So when your Vg is becomes equal to Vt, then a channel, an inversion layer will be induced here, but still there is no current flow. So if you apply some VDS here, then the current will start flowing between this drain and source terminals. So this is the mechanism of channel formation and current flow in an enhancement type of transistor. So now we will discuss the different regions of operation of an enhancement type of MOSFET. So it has three regions of operation: cutoff region, linear or triode region, and the saturation region. So when your VGS is equal to 0, then there will be no ID. So that your device will be in cutoff region. So in the linear region, when your VG is greater than VT and VDS is lesser than equal to VGS minus VT, then your device will operate in linear or triode region. So this is the equation for the ID. So here this Kn prime is the process transconductance parameter. Kn prime is equal to mu n C naught x. Mu n is electron mobility and C naught x is oxide capacitance. This C naught x is equal to epsilon naught x divided by T naught x. This is epsilon naught x is permittivity, oxide permittivity, and T naught x is oxide thickness. So if you keep on applying this drain voltage and your drain voltage becomes greater than VGS minus VT, then you can see the channel pinch off here, and the constant current will flow between source and the drain terminals. So now your device will operate in saturation region. So the conditions for the saturation region is VG should be greater than VT and VDS should be greater than or equal to VGS minus VT. So this is the equation for the ID in the saturation region. So this lambda is basically the channel length modulation. So these are the IV characteristics of an enhancement type NMOS transistor. So here you can see when your VGS is lesser than VT, then there is no current. ID is equal to 0. Your device is in cutoff region. So here you can see this is the cutoff region, and here you can see this is linear or triode region. So in the linear or triode region, VDS is lesser than equal to VOV. This VOV is basically effective overdrive voltage. This VOV is equal to VGS minus VT. So similarly, when VDS becomes greater than VGS minus VT, the device operates in saturation region. So you can see in the saturation region a constant ID will flow. Doesn't matter how much VGS you apply. So another type of transistor is the depletion type field effect transistor. So depletion type MOSFET has similar structure to that of enhancement type, but with one important difference. In the depletion type MOSFET, the channel is already physically implanted. So when you apply even a small drain voltage, the current will start to flow between source and drain terminals. So in depletion type of MOSFET, VGS is not important. It means that you don't need to apply an VG because the channel is already implanted, and whenever you apply some drain voltage, the current will start to conduct between the drain and the source terminals. So this was the difference between enhancement type and MOSFETs and field effect transistor of depletion type. So this was the lecture for today. If you have any question, please feel free to contact me. Thank you very much for today. See you next time.